Swayam Prabha. Digital India. Educated India.
Welcome to the next lecture on Organic Chemistry 3. In the Unit 1, Nitrogen containing functional groups, in the lecture 3, we will be looking at amino compounds part 1. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project was sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this session. We will start this session with basicity of amines. So, the study of amino compounds starts with the study of basicity of amines. Here we will be looking at the relationship between pKa and the basicity of amines, because knowing pKa helps us understand whether the amine is going to be more basic or less basic compared to other amines. So, this is how we are going to study the relationship between pKa and the basicity of amines. And we also be looking at the factors which will affect the basicity of amines, because the substituents which are present on an amine has a marked effect on the basicity of amines. So, we will be looking at the electronic effect, basically the inductive or the resonance effect of the groups which are attached to the nitrogen, that we will be looking at. For example, if we take alkyl amines and we compare the basicity with aryl amines, so which one is going to be more basic and why a particular type of amines, for example aliphatic amines, are more basic than aromatic amines. So, all these things we will be looking at. And then we will also be looking at the steric effect, how it plays a vital role in deciding the basicity of amines. Does it mean the number of inductive groups increases, the basicity of amine also increases linearly, or there is a change? So, that is what we are going to look into this session. And finally, what is the solvent effect? For example, the basicity of amines are different under different solvent conditions. So, that also we will be looking at. Welcome to the next session. In this session, we will be studying about amino derivatives. Let us look at the overview of amines. Amines have the general formula RNH2, and let us look at some of the reagents which are used for amination reactions. For the amination reaction, we can use ammonia, primary amine, secondary amine, like compounds can be used, and ammonium formate or formamide can also be used for the amination reactions. In some reactions, we can also use cyanides, isocyanides or acids followed by reduction. Also, some of the reagents which are used for amination reactions. Phthalimate can be used, chloramine can be used, calcium cyanamide can be used. These are the various reagents which can be used in the amination reactions. And amino compounds are actually highly useful building blocks in synthetic chemistry. Many natural products like alkaloids and other compounds contain amino derivatives. Pharmaceutical compounds, especially many drugs, have amine as the functional groups. They are also used as functional materials, agrochemicals, and in variety of organic functional group transformations. Let us look at the general structure of amines. Amines are considered as derivatives of ammonia. So, they have the general formula which is very similar to ammonia. The general structure of amino compounds are given here. In ammonia, we have all the three bonds are hydrogen attached to nitrogen atom. In the primary amine, there is one alkyl group that is attached to the nitrogen, and in the case of secondary amine, we have two alkyl groups that is attached to the nitrogen, and in tertiary amine, we have three alkyl group attached to the nitrogen atom. So, these are all the derivatives of ammonia. That is the reason we call amines as derivatives of ammonia. And in the case of quaternary ammonium salt, we have four alkyl group attached to the nitrogen atom, and the nitrogen is having a positive charge. Let us look at what is the basicity of amines. Why we need to study about basicity of amines, we will see now. If we recall what is basicity, the basic definition for basicity is, according to Bronsted-Lowry theory, the acidity of an acid can be compared with the basicity of conjugate base. So, this is the basic thing we have to remember, and let us look at the reaction. We have a amine as a base which reacts with water molecule to give the conjugate acid, that is the ammonia, and hydroxide anion is also formed. So, this is the equilibrium reaction basically. So, in this reaction we have a base and we also have the corresponding conjugate acid. So, what is the relationship between the base and the conjugate acid? The base will have one less hydrogen, that is a proton, compared to the conjugate acid. So, if we have the base as a NH2 unit, this is having a negative charge. So, if you add H plus ion to this one, so the plus charge and the minus charge get cancelled and the nitrogen is added to this NH2 unit. So, we end up with a NH3. Since a proton is added, so this is called the conjugate acid of the base, whatever the base we are talking about here. So, ammonia is the conjugate acid of the amide base. So, this is how we actually talk about conjugate pairs. And if you look at water molecule, in the water molecule, this is basically the acid unit, because if we consider this as the acid, this is basically the conjugate acid and this is the base. Base is having the negative charge here. So, the hydroxide ion is the base and its conjugate acid, that means you add H plus ion to this OH minus, we end up with a water molecule. So, this is basically the conjugate acid of the base. So, this is how we have the relationship between conjugate acid and the base. And based on the stability of the compound, we call something as the weak acid or the strong base. Say for example, water is a very weak acid, whereas its conjugate base hydroxide ion is pretty strong base. So, the conjugate base in this particular case is a strong one. When the conjugate base is strong, the acid is going to be weak. So, one of the species, acid and conjugate base, is one pair, another one is base and conjugate acid, this is also another pair. So, these are all the two pairs we will be generally talking about. So, if acid is weak, then the conjugate base is going to be strong. If base is weak, then the conjugate acid is going to be strong. So, this is the relationship, and vice versa. If the acid is strong, then the conjugate base is going to be weak. If the base is strong, then the conjugate acid is going to be weak. So, this is how the base and the conjugate acid are related to each other. So, that is what we say when we say NH2 minus is a strong base, then its conjugate acid, which is the ammonia molecule, is a weak acid. Because how do we say it is a weak acid? We already know ammonia is mildly basic. So, that is the reason when it is already a base, it has to be a weak acid. So, that is the reason we say NH2 minus is a strong base and the ammonia molecule is a weak acid. So, let us look at the ammonia molecule. In the ammonia molecule, the central nitrogen is basically sp2 hybridized and it is forming 3 sigma bonds. 3 sigma bonds with hydrogen atoms, and the lone pair is actually present in the unhybridized p orbital. So, this is the basic structure of ammonia, and when we talk about the derivatives of ammonia, that is amines, we will be looking at the structure which is very similar to this one. In other words, one of the hydrogen atom may be replaced by the alkyl group to give the primary amine. If the second hydrogen is replaced, we end up with the secondary amine, and if we replace the third hydrogen, then we end up with a tertiary amine. So, the replacement of each hydrogen atom by the alkyl group leads to substituents or the different amino derivatives. Let us look at what is the basicity of amine. According to the acid base theory, the basicity of the compound actually depends on the availability of lone pair of electrons on nitrogen for donation to a proton. So, this is how easily the nitrogen's lone pair can be donated to a proton is called as the basicity of that particular amine. So, if the nitrogen can easily donate, this is going to be a strong base. If the nitrogen cannot donate the lone pair very easily, then it is going to be a weak base. So, depending on how effectively it can donate the lone pair, based on that we decide whether it is a strong base or a weak base. And also the second thing is, this reaction is basically a equilibrium driven reaction. So, the acid and the conjugate base, these two are in equilibrium. So, when this is in an equilibrium reaction, then how the reaction, this equilibrium reaction will proceed depends on the stability of the species. If the acid is strong or more stable, then the reaction will move towards the left hand side. If the conjugate base is a more stable species, then the reaction will move in the forward direction. So, this is how we can actually decide which direction the equilibrium is going to move. Based on that, we can say how the amine is going to be dissociated. So, the ability of the nitrogen to donate the lone pair is one parameter, and the second, the stability of the conjugate acid of the amine is also the second parameter which decides the basicity of amines. Basicity of amines are basically measured in terms of pKa. Of course, many books talk about pKa, that is the acidity constant is given for the strength of the base. pKa is given as minus log Ka. Ka is nothing but the acidity constant. So, we are going to talk about the base, but we are actually going to say about the acidity of the base. So, how does it actually relate to each other? Let us look at how we can measure the basicity of the base based on the acidity of the protons. So, this is what we are actually going to see now. Why the reason we use acidity is simply because it is very easy to measure the acidity of the ammonium ions. When we talk about amines, say for example, I talk about the primary amine. So, the primary amine can be added, a proton can be added to this, which leads to the ammonium ions. So, this species can be easily studied. In other words, if we look at the equilibrium reaction, the ammonium ion when reacted with water molecule gives the primary amine and H3O plus. So, in this particular reaction we can actually measure the acidity constant very easily. So, when we have to look at the acidity constant, it is the concentration of the amine and the concentration of H3O plus divided by the concentration of RNH3 plus species. So, this ratio of the product, this is the product in that equilibrium, this is the reactant in the equilibrium. We are not using the water molecule in this particular equilibrium because water is a solvent that is used in large excess. So, its change of concentration is assumed to be unity. So, that is the reason we are not taking the concentration of water in this particular equation. So, when we measure this particular reaction, we can actually calculate the acidity constant for this particular equilibrium reaction. And we already know the Ka times Kb equal to Kw. Kw is nothing but water. So, acid plus base. So, here basically when we say acid, we actually mean this is a H plus ion, and when we say base, it is OH minus ion. So, when H plus ion and OH minus ion combines together, we end up with a water molecule. So, the acidity constant multiplied by basicity constant is nothing but the constant of water molecule. So, that is how these two are actually related to each other. So, once we know the Ka and we already know what is Kw, and from that we can calculate what is the Kb for that particular species. So, the Kb can be calculated based on Kw by Ka. So in other words, if the ammonium ion, that is the conjugate acid, is more acidic, so whenever we talk about acidity, a smaller pKa means it is going to be stronger acid, and based on that we can actually extend that. If the conjugate acid is more acidic, then we already know the base is going to be a weak one, because the strength, when we talk about whichever is stronger, then their conjugate pair is going to be weaker. So that is what is the relationship between the acid and base. And if the conjugate acid, that is ammonium ion, is more acidic, that is having a small pKa, then we can say the base is going to be very weak. On the other hand, if the pKa of a base is higher, then we can say that is going to be the stronger base, or it is going to be a much, the basicity of that particular base is going to be very high. So this is how we can say. Just remember one thing, if pKa is higher for the base, then this is going to be stronger base. Okay. So this is the only thing we have to remember. We are talking about pKa and not pKb. pKb is also used to measure, but generally for our experimental calculations, pKa measurement is much easier. So people prefer to use pKa even for the basicity of amines. So why we say pKa is actually easy to study? The reason is, it's very easy for studying pKa measurement through experimental methods. So what is the process, or what is the basic principle behind which is simply given as a substance is treated with acid or base. So we have a substance, let us say we have a amine or NH2. So this amine is treated either with acid or base. So when we treat that, what will happen is, actually there is a proton exchange takes place. So this leads to the formation of ionic species, and we can actually study this formation of ionic species using various analytical methods. And once we know this acid base equilibrium, we can actually determine the dissociation constants. Once we determine the dissociation constant, from that we can actually measure what is the equilibrium constant, and then obviously we can also study about the pKa. So the measurement of equilibrium constant can be carried out using potentiometric titration. So this is a very old method, people generally used to use this. So here we are using the equivalence point for determining what is the pKa of that particular species. And we can also do conductometric titration, because in the case of conductometric titrations we are actually using ionic species. So ions will have conductivity. So once the ions have conductivity, we can also use conductometric titration to study the formation of the ionic species. So here we will be using the limiting conductance of the species that is formed, and based on that we can actually calculate what is the equilibrium constant, and once we know the equilibrium constant, we can actually calculate what is pKa. And we can also use spectroscopic methods. So in the spectroscopic methods we can use actually UV absorption spectrometry. So when we are using UV absorption spectrometry, we are actually looking at the molar absorption coefficient of the species. Say for example, if we look at the amine and the ammonium ion, let us say we are going to look at these two species. The amine has lone pair of electron, the ammonium ion does not have a lone pair of electron. So the electronic excitation for the amine is going to be different compared to what is for the ammonium ion. So in other words, the molar absorption coefficient for amine is going to be some value, let us say if it is x, and for the ammonium ion, since it is not having the lone pair, that value is going to be different. So based on these differences, we can actually measure how much of this species is present and how much of this species is present during the equilibrium. So from that equilibrium we can actually measure what is the equilibrium constant. Once we know what is the equilibrium constant, we can actually measure pKa. So that is how, since amine, that is basically the amino derivatives, are having lone pair, we can actually make use of the laws of lone pair using ultraviolet or UV vis absorption spectrometry, and we can measure the equilibrium, how the reaction actually proceeds. And we can also use NMR titration, because each hydrogen atom will resonate at a different magnetic field strength. So, based on that, this free amine hydrogen and the ammonium ion hydrogen are going to be resonating at a different field strength, that is at ppm values. So, based on that, using NMR also we can actually measure each how the equilibrium reaction proceeds. So, this is what is called titration. Why we call this as a titration? Because we are treating this particular amine with either acid or base. So, based on that we are going to see, and in most of the cases if it is an amine, we are going to treat with the acid. Acid here basically we can call that as a H plus ion. So, addition of H plus ion leading to the formation of RNH3 plus. So, this is the basic reaction we will be studying, and for this reaction how each species, that is how much of the amine is present and how much of the ammonium species is present, we can calculate using the titration curves. And we can also use liquid chromatography or capillary electrophoresis method. So, these are basically the separation techniques. Here what we are doing is we are separating both the species, the amine and the ammonium ions are separated, and we are going to see how much each species is present. So, there are various chemical interactions that will happen because of the acid base nature or the complex formation or ion dissociation and other equilibria. We can actually measure how much quantity of the each species is present. We can measure using liquid chromatography or capillary electrophoresis. And we can also use computational methods. Of course, here this is not an experimental method, this is a computational method or in silico method. So, here based on the molecular structure, say for example here we have the amine compound, here we have the ammonium ion. So, these two have different molecular structures. So, based on the different molecular structures, we can also use computational methods to study the pKa of that particular species. How scientists measure acidity experimentally? Here is one example which is given here. So, this point, that is what we said, the equivalence point we were talking about. It is the height at half the height of this inflation point. So, this is the inflation point we are talking about. So, when the inflation takes place, half of that height is actually measured, that is the 0.5 is the value we are talking about. The half the height of this inflation point is the place we call this as the pH of this particular pH is equivalent to the pKa. Of course, there is an equation separately to find out at half the equivalence in this particular reaction, pH is going to be pKa when the dissociation is halfway through. So, this is the acidic part and this is the basic part. So, when the species is getting transformed from the neutral species to the acidic part, the half the height where the equivalence takes place is considered as pKa value for that particular species. Here is another example. We have a amino acid. So, the amino acid have both NH2 units and the carboxylic acid units. So, how we have a hydrogen which is attached to the carboxylic acid, we have hydrogen attached to the amino unit. So, these two hydrogen can have different acidity values. So, this is called pKa1 and this is called as pKa2. So, generally for amino acids, the acid proton has a pKa which is a lower pKa, and the amine proton which is basic has also, because it is a hydrogen atom, we can also measure the acidity of this particular hydrogen atom. So, the pKa of this particular amino hydrogen is always coming at higher pH. So, if we look at the equilibrium reaction under highly acidic conditions, both carboxylic acid and the amine are in the protonated form. So, this is the inflation curve, and in this inflation the pH at half the height is the one we call like a pKa at this particular species. So, the first pKa are called as pKa1 or pK1 simply is the 2.35 for this amino acid. This is nothing but the glycine, the simplest amino acid glycine. So, here the half the height is pKa for this particular dissociation. So, this carboxylic acid hydrogen is having a pKa of 2.35, and the middle portion is basically the, here we have the Switter ionic form, that means the carboxylate anion and the ammonium plus ion both are present together. So, this is called the Switter ionic species. The Switter ionic species pKa, if you want to go, if you are going to measure, here we have the hydrogen atom. So, the Switter ionic ammonium hydrogen's pKa is actually the pH 1. So, this is what is the Switter ionic pH or the pH of this particular species. And when we go to the basic conditions, so what we are actually doing is we are actually adding hydroxide anion or the hydroxide solution to the amino acid. So, the pH is getting increased, and as we are talking about the titration curve. So, when we do the titration, so what happens is we are actually looking at it can be the potentiometric titration. So, in the potentiometric titration we are getting the equivalence of this particular reaction. The pH of the solution increases slowly by the addition of the hydroxide ion, and the different equilibrium which exists at that particular time can be studied using this particular curve. So, when we move to the next higher one, what happens is we have the carboxylate anion and the amine is present. So, this hydrogen whatever is present, the pKa of this particular hydrogen is measured at 9.78. So, this is the second part of the curve, and in the second part of the curve we are looking at half the height. So, at the half the height the pH is equivalent to pKa. So, that is the reason for this amino hydrogen we are having the pKa of 9.78. So, this way we can actually study the basicity of nitrogen based on the acidity experiments. So, this is how scientists experimentally measure the acidity, and based on the acidity values, that is pKa values, we can say what is the strength of the base. So, the acidity is an indirect measure of the strength of the base. Let us look at what are the different factors that affect the basicity of amines. So, the first one is the substituent effect or the electronic effect. We have various functional groups, especially the electronic effects can be given by various functional groups. Let us look at the plus I group, because we are talking about alkyl amines. So, when we talk about alkyl amines, the alkyl groups actually have the plus I effect. So, this is the normal structure of the primary amine. So, here we have the secondary amine. So, we have one hydrogen. So, this is basically the secondary amine, and we have 3 hydrogen. So, this is nothing but ammonia molecule. So, if we are comparing the basicity of these two amines, we can actually measure the pKa of these two species. As we have mentioned earlier, when the pKa is higher, then it is going to be a stronger base. So, that is the only thing you have to remember. So, in this particular case, the secondary amine is having a higher pKa, that is 10.73. So, this is going to be a stronger base compared to the ammonia, which is having a pKa of 9.26. Now, we are talking about the alkyl group. Alkyl group can have plus I effect, as well as alkyl group also can show hyperconjugation. So, in the case of alkyl amines, basically the hyperconjugation is less important. We will see why this is less important. We already know the methyl groups have the plus I effect. So, because of that they will push the electron towards, through the sigma bond framework, they push the electron towards the nitrogen, because nitrogen is more electronegative than carbon. So, this is more electronegative. So, this pulls the electron towards itself, and the methyl group, the carbon actually pushes the electron through the sigma bond framework towards the nitrogen. So the availability of electron on this particular nitrogen is going to be high. In other words, we have to recollect what we have talked or seen about the basicity earlier. So whenever the nitrogen has more electron density, that means the ease of donation of the electron, if it is higher, then it is going to be a stronger base. Similarly, in the case of secondary amines, there are two alkyl groups, especially in this particular case we are talking about the methyl group. So there are two methyl groups which are pushing electron towards the nitrogen atom, and that is the reason the lone pair of electron availability on this particular nitrogen is going to be high. In other words, this particular amine is going to be a stronger base compared to the ammonia molecule, because here we do not have the R groups present. So there is no electron donation from the R group towards the nitrogen. So this is going to be a weaker base compared to the secondary amine. And why we cannot use a hyperconjugation for this amines stabilization? Simply because, let us say hyperconjugation happens because of the donation or bond or no bond formation. We call that as a hyperconjugation. So the bonding electrons from this hydrogen is donated to the carbon nitrogen bond. So what happens here in this particular case? So we are going to have 2 electrons on the nitrogen. We have 1, 2, 3 and 4 bonds are going to be there. So in other words, we have total 5 into 2, 10 electrons are going to be there for on the nitrogen, which is quite unstable species, because there is no empty p orbitals on nitrogen to accommodate these 2 electrons which are given here. So in other words, what we can say is the pi star antibonding orbitals on the nitrogen is having high in energy. So the sigma bonding electrons cannot be transferred or donated. In other words, the energy difference between the nitrogen's antibonding orbital and the sigma framework from the carbon are very high. So the electron cannot be easily donated to nitrogen's antibonding orbital. So this cannot happen. So this is point number 1. And second, even if it is donated, so what will happen is the nitrogen will be having a higher 5 bonds are going to be there. In other words, 10 electrons are going to be there, and the nitrogen cannot have 10 electrons in this particular configuration. So the nitrogen cannot have 10 electrons because it is only having 3 p orbital. So those 3 p orbital can only accommodate 6 electrons, and the s orbital can accommodate only 2 electrons. So maximum the valence electron can be accommodated is maximum 8 only, so not 10. So in other words, the nitrogen cannot have the pentavalent structure. So this hyperconjugation cannot exist. Let us look at the next effect, which is the electronic effect. Here we are looking at the resonance as the effect which affects the basicity. So how the resonance affects the basicity? Basically the resonance reduces the basicity. Say for example, we have an example, aniline is less basic than cyclohexyl amine. So if you look at the pKa of the aniline hydrogen, so this hydrogen is basically having a pKa of 4.6. We have cyclohexyl amine, so this hydrogen is having a higher pKa. In other words, we know that if the pKa is higher, the base is going to be the stronger one. So here we have the cyclohexyl amine having the pKa of 10.7. So this is more basic than aniline. So what is the reason for? Because both are having the cyclic 6-membered ring, and there is one bond which is connecting the carbon and the nitrogen. So in other words, if you look at the structures, except the double bonds, we have everything which is similar. So why the cyclohexyl amine is more basic? In fact, if you look at the numbers, this is actually around 6 numbers high. In other words, it is 4.6. if we add 6 to this, we are going to get a 10.6, and the number 6 in pKa is actually equivalent to 10 to the power 6 times. In other words, pKa is the measure of minus log Ka, right. So, when we talk about minus log Ka, the value whatever is each log value whichever is increasing is by the power of 10, and the difference here is a 6 number. In other words, the aniline is million times less basic than cyclohexylamine, or in other words, cyclohexylamine is million times, that is 10 to the power 6 times more basic than aniline. So, why or how this actually happens? If you look at the resonance structures, the nitrogen's lone pair is actually forming a coming towards the aromatic pi system. So, we already have the aromatic pi system here. So, this pi system is having the extension of conjugation here by the lone pair of electron. So, because of the presence of various resonance structures, this nitrogen's lone pair of electron is actually donated to the aromatic system. So, we have a nitrogen carbon double bond which exists, which reduces the availability of lone pair electron on nitrogen. So, when the lone pair availability is reduced due to resonance structure, this amine, that is the aniline, is going to be less basic compared to the other structure. In the cyclohexylamine, we do not have any resonance structures where the nitrogen lone pair can actually form or come towards the cyclohexyl ring. So, that is the reason cyclohexylamine's lone pair is freely available or highly available on the nitrogen. So, this is very highly basic, whereas in the case of aniline, that lone pair is in resonance with the aromatic system. So, it is not available. So, it is having the less basic nature. And another thing is the steric effect which we are going to see. This is also a substitutive effect which affects the basicity of amines. So, whenever there is a steric hindrance, that also reduces basicity. Say for example, if you look at the amine ammonia, we have a primary amine, we have a secondary amine, we also have tertiary amine. So, if we assume that introduction of every methyl group increases the plus I effect, so in other words, the nitrogen is going to have more electron density available on it. In other words, introduction of every alkyl group will increase the basicity of this amine. If that is the case, then the tertiary amine is supposed to be the highest basic one. This is the most basic one, and the secondary amine is going to be the second or little less than the tertiary amine. But in reality, what we see is the triethylamine or trimethylamine is less basic than the dimethylamine. So, what is the reason? If you look at the pKa value, the trimethylamine has a pKa of 9.81. In other words, this is less basic than the secondary amine, which is having the pKa of 10.73, or it is more basic. So, what is the reason for this anomaly? Whenever there is a steric hindrance, this reduces basicity. So, what is the relationship between the steric hindrance and the basicity? Let us look at the molecular structure of this compound and we will understand. So, we have already seen that the alkyl groups increase the plus I effect, or they have the plus I effect. So, they increase the electron density on the nitrogen atom. So, which in turn increases the basicity. So, the tertiary alkyl group, when they are present, that is when we have the tertiary amine, this is supposed to be the most basic one compared to the secondary amine. But unfortunately, what happens, this is the secondary amine, the structure of a secondary amine is given here. So, this is the methyl group, this is the hydrogen atom. So, this is the secondary amine. If you look at here, we have plenty of space around this particular area. In other words, this is the tertiary amine. So, if you look at the tertiary amine, there is no space for the solvent molecule, because why we talk about the solvent molecule? Whenever we talk about basicity, we are actually talking about the solution phase basicity. So, in the solution phase, if the water molecule can actually stabilize this particular species, then it is going to be the more basic one. So, as we have mentioned, the basicity also depends on the stability of the conjugate acid. So, how the conjugate acid will be stabilized? When we are talking about a solvent, the solvation by the solvent is a very important factor. So, if the solvent cannot approach this particular central nitrogen atom to stabilize it, then it is not going to be stable enough. In other words, the conjugate acid is not going to be stable. So, it is not that the amine is less basic because of its non-availability. It is the conjugate acid which is less stable compared to, in this particular case, in the case of tertiary amine, the conjugate acid is actually less stabilized by the solvent molecule, whereas in the case of secondary amines, they are better stabilized because the solvent molecule can approach from the less hindered side of hydrogen atom. So, the secondary amines conjugate acid is more stable compared to the tertiary one. So, that is the reason the secondary amine is more basic than the tertiary one. So, the steric size plays a vital role whenever there is a solvation by the solvent molecule. So, in this particular case, the stability of the conjugate acid decides the base strength. Okay. So, this is what you have to remember whenever we talk about steric reasons. The steric reason basically talks about the conjugate acid stability by solvation. Let us look at what are the other factors which affect the basicity of amines. The solvent effect is another one which affects the basicity of amines. Say for example, we have seen in the previous case the basicity strength between secondary and tertiary amines are determined by the solvation by the solvent molecule. So, whenever we have a polar solvent, this basically increases the basicity. In other words, it can actually stabilize that conjugate acid much more, due to which the basicity of the amine is increased. So, that is the reason whenever we have a polar solvent which can actually solvate the ionic species, that means in the case of let us say we have the primary amine. So, the primary amine is the carbocation, the nitrogen is having the positive charge. So, this ionic species can be stabilized by the water molecule. Let us say we have the water molecule. So, the conjugate acid, if it can be stabilized by the solvent molecule, then the base is going to be stronger base. In other words, the primary amine is going to be a stronger base. And if we look at the basicity strength in water, that is the decreasing order, we have seen that the solvation of the secondary amine in solution is very high. So, the secondary amine is the most basic one, followed by the primary amine, followed by the tertiary amine, and then ammonia. So, this is the decreasing order of strength for the amines. But if you look at the gas phase, we do not have the solvation by the solvent, because in the gas phase we have no solvent. So, when there is no solvent, then what happens? In that particular case, the basicity strength is actually the tertiary. The alkyl groups plus I effect is the one which plays a vital role. So, we have two important parameters in the case of alkyl amines. So, one is the plus I effect of the alkyl group, which increases the basicity. The second one is the solvation or the stability of the conjugate acid. Solvation stabilizes the conjugate acid, so the basicity increases. So, we have two effects operating to increase the basicity. In solution phase, both these operate, but in the case of gaseous phase, only this particular, that is the plus I effect, operates. There is no solvation effect which stabilize that amines in the case of gaseous phase. So that is the reason in the gaseous phase the trialkyl amine is the most basic one, followed by the secondary, followed by the primary, followed by the ammonia. And there is one more thing we have to remember: whenever we are measuring the basic strength, we have to look at what is the medium in which we are using. Basically we are talking here about water, but we also have other polar solvents like DMSO and other polar solvents are available. So depending on what is the solvent that is being used, the polarity actually will change. That is because the solvation effect changes because when we change the solvent. So let us look at the pKa of alkyl ammonium ion derivatives. Here we have the equilibrium reaction between ammonia and H3O plus, which gives the ammonium ion as shown here, and for this particular species the pKa is 9.26, and when we have the primary amine we have the pKa of 10.66. When we have the secondary amine the pKa is 10.73, and when we have the tertiary amine we have the pKa of 9.81. So if you look at the basicity which is plotted against the strength of each amines, so the ammonia is having the lowest pKa. In other words, this is less basic, where it increases to primary amine drastically, and it further increases little bit more to the secondary, and for the tertiary it actually drops. So pictorially you can actually follow this. This is because of the steric reason. So in the case of tertiary amine, the steric inhibits the stability of the conjugate acid, which reduces the basicity of this particular tertiary amine, whereas the secondary amine and the primary amine are highly stabilized. The conjugate acids are highly stabilized by the solvation, so they are more basic. Let us recollect what we saw about the alkyl ammonium ion and hyperconjugation. So we have seen earlier also that hyperconjugation actually does not stabilize the ammonium ion. So we are just going to reiterate the same thing. In the case of inductive effect, the plus I effect groups actually push electron towards the ammonium ion. So this is more stable compared to the less stable pentavalent one, because here the nitrogen is pentavalent. In other words, the nitrogen cannot have more than 8 electrons. So that is the reason this is quite unstable structure, and that is one of the reason between NH3 plus and trialkyl nitrogen plus ions, the NH bond will be more polar in the case of ammonia only. So in other words, the electron density on nitrogen is going to be higher in the case of ammonia than this trialkyl ammonium ion, because the trialkyl ammonium ion actually has a quite unstable pentavalent structure. So hyperconjugation cannot stabilize this particular ion. So that is the reason this ion is going to be less stable. Let us look at the basicity of amine versus amide. Amine and amide both has the NH2 unit. If you look at here, we have the NH2 unit is common in both the cases. So when NH2 unit is common in both the cases, if we look at the pKa, the primary amine is that is the methylamine is having a pKa of 10.6, which is quite high compared to acetamide, whose pKa of this hydrogen is around 0.63, which is very low. In other words, this amide is going to be much more less basic than the primary amine. So what is the reason for this? We are going to look at here. We know amine is a basic one, on the other hand amide is a neutral one. So if you look at the electrostatic potential map, the red color actually shows more electron density, blue color shows less electron density. So this is the methylamine. So if you look at this is the nitrogen atom. So in this nitrogen atom, the red color is very huge. In other words, the electron density of the nitrogen is very high. In other words, this nitrogen is more basic in nature. So that is what it implies. The electron density high means it can easily donate that electron and it can act like a strong base. And if you look at the acetamide, you look at the negative the electron density, this is more on the oxygen atom. So we have the oxygen atom, and this oxygen atom is having more electron density, and if you look at the nitrogen atom, this is actually having close to the blue color. In other words, the electron density on this nitrogen is very small. In other words, we can say this nitrogen does not behave like a base because it is not having its lone pair of electron. So what happens, or why this is not having the lone pair of electron? If we look at the resonance structures, basically the lone pair of electrons are actually in resonance with this particular electronegative oxygen atom. So the electronegative oxygen atom pulls the electron towards itself, making this nitrogen N plus. So when it exists as a N plus ion, it is not having its lone pair of electrons, so the nitrogen cannot behave like a strong base. So that is the reason amine is more basic, because the nitrogen's lone pair is freely available, whereas in the case of amide, those lone pair of electrons are not available on the nitrogen, so this amide is highly neutral in nature. So let us look at some of the amines which are used as a bases in synthetic preparations. So we have various amines which are shown here, which are generally used as bases in organic synthesis. The first one is N,N-dimethyl The N,N-dimethyl aniline is having a pKa of 5.15. And we have pyridine, which is little bit more basic than N,N-dimethyl aniline. The pKa is 5.3. So when the pKa increases, we already know the basicity also increases. The next higher base which is used is the imidazole, which is having a pKa of 6.8. And commonly used bases are triethylamine and N,N-diisopropyl ethylamine are the Hunix base. So they are having a pKa value of around 10 to 11, close to 11. So these are all the common bases which are used in many organic chemical transformations. And we also have other amines, bicyclic amines. We have DAPCO, DBN and DBU and DBN. These are having a higher pKa. So basically DBU and DBN are having much higher basicity compared to even the N,N-diisopropyl ethylamine, or this is generally called as DIPEA. So diisopropyl ethylamine. So this is a very common base which is used in synthetic organic chemistry for various preparations. Let us recap the summary what we have studied so far. We have studied about the basicity of amine. Before we study about what are amino compounds, the most important thing is the basicity of amines, because amines are basic in nature. So what are the factors which contribute to the basicity of amines we have seen. We also studied about the relationship between pKa and the basicity of amine. Of course, you have studied pKa is basically the acidity constant, and how the acidity constants are related to the basicity of amines we have seen. The higher the pKa value leads to the higher basicity of the amines that we have seen. And we also have studied about the various factors that affect the basicity of amines. Say for example, when we studied the substituent effect, we first started with the electronic effect, that means inductive and resonance effect, how they affect the basicity of amines. The first one is the substituent effect. So here we studied about how the electronic nature of the substituents, basically the groups which are attached on the nitrogen, affect the basicity. We studied about the inductive and the resonance effect. For example, when we look at alkyl amines are more basic than aromatic amines. The reason is, in the alkyl amines there is no resonance effect operating, and alkyl groups are also plus I effect group, that is positively they donate electron towards the nitrogen, which makes the availability of electrons on the nitrogen very high. So that's why aliphatic amines are more basic compared to the aromatic amines we have seen. And we also studied about the steric nature of the substituents, basically when we move from primary, secondary and tertiary amines, how the basicity changes, that also we have studied. Although there is no linear relationship, because if the plus I effect group, that is the inductive effect group, increases, obviously the nature or the basicity of the amine increases, but that is not actually observed. In reality, what we see is when the crowding increases on the nitrogen atom, basically the availability of the nitrogen, that is the solvation effect, is actually reduced, due to which the tertiary amines are less basic than the secondary amines, that we have seen. And finally, we have studied about the solvent effect, how the solvent effect affects the basicity of the amines, because if there is a solvent effect, then obviously the solvation plays a vital role in deciding the basicity of the amine. When there is no solvent, especially in the gas phase, the basicity strength is actually decided by the number of inductive effect groups only. So, these are all the things we have studied. With that, we conclude this session on the basics of amines, that is the basicity of amines. Thank you.